We want to talk about the Pearson's product moment correlation coefficient. Pearson's product moment correlation coefficient. How do we get the Pearson's product moment correlation coefficient? So the Pearson's product moment correlation coefficient is denoted by rho. It's denoted by rho. So sometimes the rho is like that, isn't it? Are we together? So the Pearson's product moment correlation coefficient is denoted by the rho. You can use that. And it is given by the covariance of xy over the square root of variance of x by variance of y. Square root of variance of x is like standard deviation of x. Square root of variance of y like standard deviation of y, isn't it? Because you know very well laws of indices, root a times b is the same as root a times root b, isn't it? So square root of variance of x times variance of y is like root bar x times root bar y. I think those are standard deviation. Now, if the variance, for instance, the variance of x is given by what? The average of the squares of the difference of the values with the mean. That is the summation of the x minus x bar squared, isn't it? Over n, isn't it? So let me use this. These are small values of x. Let me let these ones to be capital to differentiate. Then the variance of x, variance of y is going to be the summation of the average of the squares of the difference of the data values to the mean. That is how to get the variance of y, isn't it? Are you together? So it means the covariance of x and y is going to be given by what? So you can see here, when it is x minus x bar squared, it is like saying this is summation of x minus x bar times itself, x minus x bar over n, isn't it? So in covariance, this is the same as y minus y bar multiplied by itself, isn't it? Now covariance of x and y, one of them is for x and the other is for y. So it means it will be summation of x minus x bar, then the second part becomes for y. Then it is now y minus y bar over n. So if it is x alone, then that one becomes xx, then it turns out to be x squared, isn't it? If it is for y alone, it becomes variance. Then y, then it becomes squared. Are we together? Now from here, if you now substitute, if you let this x minus its mean to be small x, if you let small x to be capital X minus x bar and small y to be capital Y minus y bar to be denoted by small y, isn't it? So what are we going to have as the variance of x? So the variance of x is going to be what? Summation of small x squared over n, isn't it? Because x minus x bar, we said let it be small x. So that is small x squared. See there? Then the variance of y is going to be y minus y bar, you said let it to be small y, isn't it? So this is going to be summation of small y squared, isn't it? Over n. Then the covariance of x and y is going to be summation of, this is, you say to be small x, and y minus y bar, you say to be small y. So that is xy, small x, small y, isn't it? Over n. So from there, if you substitute these values in the formula here, where there is covariance of xy, you put the value of covariance of xy, which is summation of xy over n, then it is over square root of Variance of x is what? Summation of x squared over n. Summation of x squared over n. Then variance of y is what? Summation of y squared over? Summation of y squared over n. So look at that. Now if you look at that, what do you see? You now see the correlation coefficient rho is going to be given by what? Summation of xy over n divided by n times n is n squared, isn't it? See, when you get the square root of n squared, you get n. So it means we are going to have there the square root of summation of x squared times summation of y squared over n. Because n times n is n squared, and you can get the square root of n squared, you remain with n, isn't it? Isn't it? See, n cancels with n, isn't it? N cancels with, so you get the covariance, the Pearson'S correlation coefficient to be summation of xy over the square root of summation of x squared times summation of y. So that is the formula for the Pearson'S product moment correlation coefficient. So if you are told to find the correlation coefficient, then we are looking for the Pearson'S product moment correlation coefficient. So how do you now use coefficient to state the relationship? The correlation coefficient is like a gradient. It is like a gradient. Now if you have something like this, let me say this is a Cartesian coordinate system. If you have all points, if you have the points are scattered, a case of a scatter plot. If you have a case of a scatter plot, in a scatter plot, you cannot draw any straight line from it, isn't it? So in case of a scatter plot, there is no gradient. And if there is no gradient, we say when there is no gradient, then that means there is no correlation between those variables. So if this is the y-axis, x-axis, meaning the relationship between the y and x values, isn't it? So when there's no gradient in case of a scatter plot, then we say there's no correlation. That measure correlation is like a case of a gradient of a straight line. Are we together? Is that okay? Then you move to the next one, the next case, when you have all the points on a straight line. If all the points are on a line, none of the points in that plot is outside, they are forming a straight line. All the points are captured in a straight line. So if all the points are captured in a straight line, then that is said to be perfect. Are you seeing that? Are we together? If all the points are captured in a straight line, then the correlation is said to be perfect. So we say that there is a perfect correlation. A perfect correlation. And if all points lies on the straight line, it means the gradient will be what? The gradient will be 1, isn't it? The gradient will either be positive 1 or negative, because all the points are on the straight line, isn't it? Are you seeing that? Because when you say if x value is 1, y value is 1. If x value is 2, y value is 2. If x value is 3, y value is 3. Then you find all those points are on the straight line. So when you get the gradient, you find the gradient to be positive 1. Are you seeing that? Are we together? So when the gradient is positive, then it implies what? The gradient is positive 1. 1 implies perfect, meaning everything is on the line. No point is left outside. Are you seeing that? Meaning if no point is left outside, the gradient must be 1, and that is what means perfect, isn't it? So when that gradient is positive, then we say it is a positive correlation. When the gradient is 1, it is now a positive perfect correlation. Are we together? And the positive is sometimes said to be direct. Are we together? Positive is sometimes said to be direct. So it means when you get the gradient to be positive, then it means there's a direct correlation, or there's a positive correlation. Then when that gradient is 1, it means all points were aligned on the straight line, so it is said to be perfect. Are you seeing that? So in real, at the end, what definition will you, what will you deduce from that? You say there is a direct perfect correlation. Are you seeing that? There's a direct perfect correlation between those two variables. Are we together? Is that okay? So just with the same case, if you now have the gradient is 1, all the points are lying on the straight line. If you have all the points are lying on the straight line like that, then that will mean the gradient will be 1. Perfect, isn't it? Yeah. But now, the gradient in this case, if you look at this case, if you find the gradient to be negative, you know that gradient getting 1, when you don't deal with the sign, when you leave sign alone, that one alone shows all the points are on the line, isn't it? So when it is negative, it is said to be negative or inverse. Are you seeing that? Are we together? So when the gradient is 1 and it is negative, negative gradient implies what? It implies negative or inverse. So the moment the gradient is 1, that is perfect. Negative means inverse or negative, just like that, isn't it? So you say there is a perfect inverse relationship between x and y. Are we together? So if y values were maybe for mathematics and that you say there's a perfect relationship, there's a perfect negative relationship between the maths and physics if you are measuring those given variables. Are we together? Are you seeing how these things are defined? Are we together? Yes. So it means it is the gradient which is guiding you to know how is this. So it means when the gradient is 1, it is perfect. If the gradient is greater than 0.5, around 0.7, that is, you can just use the word good, isn't it? There's a good relationship. Are you seeing that? And when it is below 0.5, around 0.5 there's fair, isn't it? Isn't it? Good, there's fair. So it means the moment you get the gradient to be positive 0.7 or positive 0.6 is below 0.7, isn't it? So positive 0.6, positive means direct, isn't it? So you see, there's a direct fair relationship, isn't it? So above 0.7 you say good, isn't it? So if it is positive 0.7 or 0.75, if you get a correlation of positive 0.75, you say positive means direct, isn't it? So there's a direct, there's a good direct relationship between those two variables, relationship or correlation, isn't it? Are we together? Are you seeing how it is defined? So 1 means perfect. Anything between 0.7 towards 1, that is good, isn't it? Meaning from 0.5 towards 0.7, that is fair, isn't it? Below 0.5, that is low, isn't it? Are we together? Negative is inverse, positive is direct. Are we together? You can as well say there's a negative relationship or there's an inverse correlation between this, isn't it? Are we together? So that is how to comment on the relationship, okay? So when you are told to determine the correlation coefficient between the two given values and you comment on the relationship, when you are commenting on the relationship, you must note that correlation value, that gradient. Is it perfect? Is it good? Is it fair? Is it low? Isn't it? Then when it is positive, that is direct. When it is negative, that is inverse. Are you seeing those are all the terminologies you are using to comment on the relationship, isn't it? Are we together? So that is how to deal with the Pearson's product moment correlation coefficient. Let us look at example 1. The first case, example 1.